Hello everyone and welcome back to my channel. So it's been a while, but today we are going to see something very interesting. So today we are going to see how to do fault detection in industrial processes. So for that case, today we are going to take a data set which is a simulated data set, but the simulation is pretty realistic, which there has been many people published on this Tennessee Eastman process, which is a very well-known chemical process. So what they have done is they simulated this dataset, and this dataset has been used in many research papers for benchmarking. So this is the benchmark of anomaly detection dataset for data-driven method. So today we are going to use this dataset, and first we'll know about this dataset, what this dataset has to offer, what is the split, what is the training data, what is the testing data, what are the faults, so basically, we'll try to get an idea of what this data set is, and then we'll look further, like how we can do, again, how we can design a fault detection algorithm. For now, we'll start with very basic. We'll start with the statistical method in this part one, as you have already seen the thumbnail. We'll use just basic statistical method, and then we will graduate up to machine learning, deep learning, and further and further. We'll also explore the XAI, which is the explainable AI domain as well, using this dataset only. So yeah, so this is the Tennessee Eastman process. Uh, and what we have in Tennessee Eastman process is a chemical plant. This is the entire chemical plant that we have. This is the chemical plant we have. And from the plant, we continuously get some data. And for the dataset, I have got the dataset from this Kaggle website where the dataset is open source and you can just download it. And it's like 1 GB. But along with that, I'll give you another source, this one, finding process fault, exploring the TEP. So here they have explored the dataset very well. They have given what each fault means, how can you interpret that, and they have shown some basic fault detection methods as well. So your first task is to go to here and download the dataset, and the dataset looks like this. It is not a Python file. You don't expect to see it in a Python data frame, but this simulation was done in R. So this all the files are in R data frame. And our first goal is to convert this R data file into Python so that we can do our processing in Python. And so that what I've created this Jupyter notebook, and this is an important library you'll need to install. Maybe you don't have that. It's called PyReader, and this PyReader will help us to read the R data file in CSV format. So, and these are rest are the usual libraries we always import, like Matplotlib, Seaborn, NumPy, and Pandas. Well, so give a brief introduction. We'll go to the, I've created a PPT. We'll go to the PPT to explore these details even more. So for now, the TEP stands for Tennessee Eastman Process, which is the process that we are exploring right now. So from column 4 to 55 are the variables or the sensor readings, sensor measurements. And each sample was collected in between 3 minutes. And for the training dataset, it was done for 25 hours, and for the testing dataset, it was done for 48 hours. For the training dataset, the fault were introduced after 1 hour into the system, into the once the simulation has been started, and for the testing dataset, it was started after 8 hours. Okay. For now, what we're gonna do is first you list the function PyReader, and we'll import read R, so it will read the R data file, and we'll give it the location from where you have the data file in your system. And then this is the key. This is the key within this. So I'll show you. I'll just copy this and yeah. So you see, this is how the JSON looks like, and this is the key that we need to extract. So that's why I'm putting this key here, and this is for the faulty training set as well, so that after you get the key, you directly get the data frame itself, like this. So now you get the data frame, which is our convenient, which is very convenient for us. So I did that for DF fault free and DF faulty. Okay, and then what I did, I concatenated them both. Fault free has only data for fault free case, and faulty has data for all different kind of faults. Okay, so now that we got a feel of what the dataset is, let's see what this dataset contains. Okay, so in the Tennessee Eastman process, we have the power plant here and we get some sensor reading. In this case, we have 52 or 53 sensor values. Doesn't matter. We don't need to know what goes inside the processes. If we know, that's even better. But for now, we're just going to analyze it in a perspective of a machine learning engineer. All right. So yeah, and what is the big picture? What do we want to do? So this is our system. We get sensor values from there. Using this sensor values in an unsupervised method, we want to do anomaly detection. So when there is a fault, we should be able to detect it using our algorithm. And we don't need any label data because this is an unsupervised learning. And the dataset is taken from the Kaggle website here, which I'll give link with the video. And the dataset has looks like something this. They are all R files. Okay, this is the a screenshot of the dataset that we just saw. The first one is fault number, simulation run, sample, and yeah, these are from XMEA-S1 to the last one. They are like 52 sensor values. So this is the fault, the different type of fault that has been introduced, and 20 different type of fault were introduced in there, indeed. So in the first case, we have fault number 0, which is uh, which is basically the fault-free condition. And in this fault-free condition, we have different simulation run. So in every simulation, you need to give some initial condition. In this case, the initial condition can be how much amount of material reactants are already in the tanks, something like that. And in different random initialization, they run this simulation for 500 different times. And each time you have a different result. So using simulation run 1, and each simulation run has 55 variables that has been monitored for 25 hours. And if you plot this according to sample number, you get something like this. And same has been done 55 different sensor values. And same has been done for 500 times for each fault scenario. So that is an extensive amount of data we have from the simulations, which we can use for our analysis. I hope that is clear by now. Let's see introduction of fault. What time fault was introduced? So in the training data, which we are going to concern for now, it has 1 hour. 1 hour into the simulation, they have introduced the fault. So what does that mean? Is the sampling rate was 3 minutes. If you divide 1 hour by 3 minutes, then we'll get 20th sample onwards. We get the fault. So this the green line represents when the fault has started. Basically 20th sample. In the x-axis, you have the sample number, not the time, but the sample number. All right. So for this first video, we are going to use a basic statistical method for fault detection, and we are only going to use the fault-free condition for that. So what do we have here? In fault-free condition, we have different simulation run 1, simulation run 2, up to simulation run 500. So we will get this is first variable. I'm calling them x1. And similarly, you have like 52 variables. So what I'm going to do, I'm going to take the first variable from 500 simulation run and plot it in a histogram like this. I am assuming that they belong to a normal distribution and I'm plotting them like this. And then I want the mean and standard deviation of this first variable. I'll call that mu1 and sigma 1. Same thing I'm going to do for each and every variable present in my fault-free dataset. So I'll have 52 mean variables and 52 standard deviation variables. So let's see how we are going to do that. So this is our data frame, which has all the data. And next, we're going to do data visualization and for the fault-free case especially. So what I'm going, PP is just like a temporary data frame, just for plotting sake. So what I'm going to do, I'm going to take my data frame, and in the data frame, I'm going to filter that the fault number should be 0, that is the normal case, and I'm going to see for the first simulation run how my data looks like exactly. and then I'm just going to plot it. So here we can see that this is for the first variable, for the second variable, third, fourth, fifth, sixth, so on and so on. So you get a lot of variables for just one simulation run, and this has been done for 500 times, this simulation run. All right. And then next, what I'm going to do, I'm going to see how the distribution looks like for different simulation run for a single variable or single sensor data. So in this case, I'm choosing my um, column or my sensor data to be XMEA3, this one, and I'm going to change different simulation run, like simulation run 1. How does it look for this sensor variable? You can check, you can change this to any sensor variable. You can check this one, this one, this one, whichever one you prefer, and just see how it look, how it differs from different sample, from different simulation run. All right. So what I did is I did a range from 1 to 500 with a gap of 50 so that I don't have to wait for a long time. So this is for simulation run 1. This XMEA value looks like this. For the range, you can see that it belongs to 440 to 460 in this case also. The simulation run 51, it's same. For 101, same. The range is basically the same. That's what I want to see. And that for different values, we can just change that one to, suppose I want the first variable, XMEA1. So yeah, here also, here you see there is a big range in different between different type of sensors. So first sensor has a range from 0.2 to 0.3, whereas the previous one had 1000. That gives us an idea that when you try to do machine learning, you need to scale these values, otherwise it will be difficult for machine learning to converge. Yeah, here also you can see that see, the first sensor has a range from 0.2 to 0.3. The second one has 3600 to like up 3000, then other has 4000, then 9, 10. So yeah, there is a big scale difference in individual sensor values. So we need to take care of that when you do machine learning. But for now, it's good. It's well and good. Well, now we did the visualization of how our data looks like. Now what we're going to do, we're going to calculate the basic statistics, the mean and standard deviation. For that, I'm going to create a temporary data frame, normal data, where I'm going to take the 500 simulation run data only for the normal condition. I'm going to take all the data from the normal condition, fault number 0, which is the normal condition, into the normal data frame. And if I see how the normal data frame looks like, yeah. So in the normal data frame, I also like deleted the first three column because I don't need them for the analysis. And this is the normal data. So all right. So what I'm going to do, I'm going to take the uh, mean and standard deviation of each column, and then I'm going to analyze this. So calculate the of each variable or each column. So using this mean and standard deviation of the data frame, of the pandas data frame, we can just get the mean and standard deviation. And then what is upper limit is so mu plus 3 sigma will be your upper limit, which will correspond to 99% of your normally distributed data, and mu minus 3 sigma will be the lower limit. So our data should in the normal scenario, it should range between this 6 sigma range. Okay, I think that is clear now. So upper limit is mean plus 3 standard deviation corresponding to 99% of the data, and mu minus 3 standard deviation. All right, so normal data is this, and then what we're going to do is now it's the interesting part. This thing we already got, upper limit and lower limit. So let's see what is my upper limit is. My upper limit should be it is a 52 length variable where it captures the upper limit of each variable. Each variable is in each sensor data, and same is for lower limit. And now what I'm going to do, I'm going to use this upper limit and lower limit to do a monitoring. Well, so what I'm going to do, I'm just again importing the normal fault state, but right now I'm just importing the simulation run 1. I'm not going to other simulation. You can just change the simulation run value here 1 to 500 and you can check for yourself. And then I'm plotting this. So first I'm creating a axis which will correspond to, because I have 52 sensor value, I'm taking subplots 13 cross 4. And for each plot, I'm going to populate with the corresponding variable. So what does, so in this, all the variables, these are for one single run, single simulation run for 52 variables of the normal health condition. And in normal or fault-free condition, the red one belongs to the upper limit, the bottom red one belongs to the lower limit, and the black one at the center represents the mean. So if your process control, if the process variables, if these 52 process variables are within this red line, that means it's the normal condition. If they cross this, like here you can see, though it is a normal condition, there is uh, some they're overpassing the threshold and giving us a false alarm. So that we need to consider also. And here you can see these are the 52 variables for one simulation run, and most of them are lie within the defined upper limit and lower limit. We can change that to simulation run 2 also. It should work fine. Don't worry, it takes a little time, but yeah, no problem with that because the DF is a huge one. I think it's like 400 MB. Yeah, for the simulation run 2 also we can see that yeah, most of like here it's under, here it's under the limit, here it's little outside the limit, and things like that. Yeah, you can check, but the main idea is that they are mostly within the limit. So for now we can see that the statistical method that we have developed is well able to identify the normal fault condition just by using normal distribution principles. And now it's time to see how it performs on a faulty case. For the faulty case, what I'm going to do, I'm going to filter my data frame according to fault number 1. That means the first fault scenario, or just one simulation run, like the first simulation run. It doesn't matter, you can change it and see. And I'm going to do the same plotting, but right now what we can see is, look at here. The process instantly deviates. So here this green line represents the time when the fault was introduced, that is the 20, and suddenly after that you see there is a deviation of fault that crosses the thresholds. So you can see, okay, there is a fault here, but for the second variable doesn't pass that much. So there are some variables which have higher impact on this kind of fault compared to other. So let's see. So this variable, you see, it instantly surpasses the threshold. Same as this one here, this one as well, this one as well. So yeah, we can see. Let's go and see some different fault 2. Yeah. So also for fault 2, yeah, here this variable surpasses the threshold, and we can detect fault 2 as well just by using normal statistical method. But I think the fault 3 was the very difficult one, where it's really challenging to detect that compared to fault 1. For normal condition, the fault 3 is very similar. So let's see. So coming to, yeah, in fault 3 we can see that most of the variables are lying underneath the thresholds. In fact, none of the variables are surpassing the threshold that we have already defined. So it's going to be pretty difficult to identify this fault just using statistical method. And also there is another problem that I'm going to discuss here. Is right now what we saw is for each case we have to look at 52, 55 or 52 different variables at each time, which is not feasible for a human being to comprehend and look at all the 52 variables at one time. So what we want to do is each time t, we want to combine this 52 variables into single process parameter. So which will give us the quality of the process going on at that time, whether there is a fault or not. And let's see how we are going to do that. So threshold testing for fault detection. This normal distribution curve I put here just for the reference, mu and 3 sigma. So what we have right now, we have the upper limit and lower limit value for all the different type of variables, sensor variables of the process. And let's say we get a new variable at time t, which we need to do, which we need to say if this belongs to faulty state or healthy state. So at time t, we get, let's say 52 process variables, x1, x2, and x52. Then what we do, we do a threshold testing. What is our threshold? UL1 is our upper limit and LL1 is our lower limit. We need to check that if our this x1 variable passes the upper limit or it's lower than the lower limit, that will indicate fault. If this is true, then it will indicate fault. Same we do for x2 variable. We have upper limit 2 and lower limit 2, and same for all the variables. So now what happened is this will give 1 or 0, 1 or 0, 1 or 0. Now we can combine this all by using a OR condition. That means what? If any one of the variable has passed the threshold, indicate that there is a fault. So by using this simple method, we can combine all the decision into a single method. So this entire part will output 1 or 0. Even if one variable has passed a threshold, it will give 1, because that's important for us, because the fault is important. If there is a fault, it should not say there is no fault. All right. So yeah. So by using this simple method, we can combine the 52 variables decision into a single one or 0, whether there is a fault or not. So now let's see how we can do that. So for that, what I did is, yeah, it's very hard to look at 55 variables at the same time. So we can combine them to create a single array of any variable. It goes out of bound, it will generate 1. That means there's a fault condition. So for that, I created this function. Let's see what this function does. So I have the temp TF. So this is the temp TF that I just created in this previous case, this temp TF from a different fault scenario. All right. So I'm using that temp TF, and then what I'm putting my condition. The condition I show, if it is greater than upper limit or it is less than lower limit or condition in between, I get the decision, and then using np.any, that will combine this decision all together. Okay, let's see what does that mean. So I'll just copy and paste this one. So yeah, so now we did a checking like for all the variables, and then what do we do? So yeah, so now we see that for all entire 500, so entire length of the data, we get we get the final result. It says false. The statistical method says false for this condition, and then I'm just converting the Boolean value into float. So that's it. So I'm writing a for loop. In this for loop, what is happening is I'm enumerating through different fault numbers. Fault 0 means the normal held condition, and up to 20, like up to 20. This will exclude the last element. And I'm going to, in a temporary data frame, I'm going to dump the value of that fault number, and I'm going to see how the performance is. And this fault check is the result of this combined result function that we just created. So which will take the decision of 55 variables and combine it to one. All right, and then I'm just plotting it, and I'm just plotting a scatter plot for the using the sample as the x-axis and fault check as your y-axis. All right, and all right, that's it. So now we can just run this one. So for fault number 0, we have some this false alarm rate. That means there is no fault, but our algorithm is saying, okay, there is fault. So yeah, uh, this is one disadvantage of this method. And for fault number 1, it's accurately able to identify. So as soon as the fault has happened, the green line suggests when the fault has occurred. Our algorithm is able to detect it pretty accurately. For fault number 2, also it's pretty easily able to detect. But fault number 3, it's not at all able to detect. It's same. It thinks fault 3 is normal fault condition itself. And for fault number 4, yeah, very nice. Fault 5, not that much. Fault 6, nice. Fault 7, nice. Yeah. So yeah, you can see for different type of fault how it's performing, and it's even difficult to like get a single matrix like how it is performing. So what I'm going to do is I'm going to create a single matrix F1 score. Basically, this is a better accuracy matrix than comparing just the accuracy. That's what I want to say. All right. So what I'm going to do in this here is I'm going to write a function and I'm going to enumerate through for all the different type of faults, the same one that I did here. The same one I did here is I'm going to enumerate through different fault types. I'm going to put them in a file put them in a data frame. Then I'm using the combined result to from the using the data frame, and it has two other input also, upper limit and lower limit, to do the threshold checking, and I get y pred, which is a single variable for each time instant. And I'm saying if f num equal to 0, that means if it is the healthy condition, then my true label should be 0. And else if it f num is not equal to 0, it belongs to any other fault, then my y true should be 1. But for the first 21 sample, it belongs to 0 because the fault was introduced after 20th sample. All right, so I thought this part is clear. And now let's say now it's just importing some matrices. So I import f1 score from scalar. Then I do true. This is the true value, and this is the pred, the one predicted by my statistical method. And I'm averaging by macro, and I'm printing the f1 score. Then I'm just printing the confusion matrix as well. People who are acquainted with confusion matrix, it will be easier. So I'll just run this. And yeah, you can see that the F1 score for fault number 0 is 0.47. Well, not that good, not that bad. We can see that most of the 0 condition it's able to classify. The fault free condition has all the, like there is no fault in a case actually there. So all belongs to 0. But there it is predicting some cases as fault. Okay, that's okay. But fault number 1, we can see it has a very high F1 score. For fault 2, it has very high F1 score. But fault 3, it has very low performance. It's doing a lot of misclassification. For fault 4, yeah, very good. Yeah, so basically we can see that there is pretty good performance just by considering the statistical method. So that was all about this video, and in the next video we are going to use principal component analysis in an unsupervised way to do anomaly detection. So yeah, I hope I'll see you in the next video.